Imagine a planet, not orbiting a star, not warmed by sunlight, not part of any solar system, just drifting through the absolute darkness of interstellar space alone for billions of years. In 2021, astronomers using the optical gravitational lensing experiment discovered something that redefined our understanding of planetary systems. A world roughly the size of Earth, traveling through our galaxy at 45 kilometers per second, untethered to any star, completely alone. They named it Ogle 2016 BLG 1928. But here's what keeps astronomers awake at night. This wasn't a rare discovery. Statistical analysis suggests that there are more rogue planets drifting through the Milky Way than there are stars. Think about that. Our galaxy contains approximately 400 billion stars. The evidence suggests there may be 2 trillion rogue planets wandering the cosmic void. 2 trillion worlds. An eternal night. Many larger than Jupiter. Some possibly harboring life in vast subsurface oceans, warmed not by a distant sun, but by the slow decay of radioactive elements deep within their cores. What if most planets in the universe never see a sunrise? What if the default state of a planet isn't to orbit a star, but to wander forever through darkness? What if Earth itself could be ejected from our solar system, cast into the void, joining this invisible ocean of orphaned worlds? Today, we journey through evidence that challenges everything we thought we knew about planetary formation, the nature of solar systems, and the possibility of life beyond Earth. Prepare yourselves. We begin. The story begins in 1995, not with a deliberate search for rogue planets, but with an attempt to find something else entirely. Dr. Shigeru Ida at the Tokyo Institute of Technology was running computer simulations of early solar system formation, trying to understand how planets achieve stable orbits around their parent stars. What he found was chaos. In simulation after simulation, planetary systems didn't settle into neat, stable configurations. Instead, they experienced violent periods of instability. Newly formed planets gravitationally scattered each other. Large worlds migrated inward, disrupting smaller planets. And in nearly every simulation, at least one planet was ejected entirely, flung out of the system at escape velocity, destined to wander interstellar space forever. Ida published his findings, expecting them to be dismissed as computational artifacts. Instead, they triggered a revelation. Planetary ejection wasn't a rare catastrophe. It was a fundamental part of how solar systems evolve. To understand why planets get ejected, imagine a game of gravitational billiards played over millions of years. When planets form from a protoplanetary disk, they don't emerge in stable orbits. They interact gravitationally, pulling on each other, exchanging momentum and energy. If 2 planets pass close enough, their gravitational interaction can dramatically alter their orbits. One planet might fall inward, toward the star. The other gets flung outward, gaining velocity. If it gains enough speed, reaches what astronomers call escape velocity, it breaks free of the star's gravity entirely. This isn't speculation. We've observed this process happening. In 2012, astronomers using the Gemini Observatory captured images of a young star system called GU Piscium, showing what appeared to be a massive planet on a highly eccentric orbit, likely the result of gravitational scattering that would eventually eject it completely. But here's where the story becomes deeply strange. Finding rogue planets should be nearly impossible. They don't emit light, they don't orbit stars, so we can't detect them through the transit method or radio velocity measurements. They're invisible against the cosmic background, wandering unseen through the darkness. Yet, astronomers found a way: gravitational microlensing. Einstein's general relativity predicts that massive objects bend space-time, creating a gravitational lens that magnifies light from background stars. If a rogue planet passes between Earth and a distant star, its gravity will briefly brighten that star's light, a telltale signature lasting hours or days. In 2011, Dr. Takahiro Sumi led a team using data from the MOA project in New Zealand. They analyzed microlensing events that showed extremely short duration, too short to be caused by stars, too massive to be asteroids. The only explanation? Jupiter-sized planets with no host star drifting freely through the galaxy. The initial discovery identified 10 candidate rogue planets. Based on the survey volume and detection efficiency, Sumi's team calculated there could be 2 Jupiter-mass rogue planets for every star in the Milky Way. 800 billion rogue giants, each large enough to have been a star if it only had accrued slightly more mass. The astronomical community reacted with skepticism. Surely the detection methods were flawed. Surely these were planets in extremely wide orbits, still technically bound to distant stars, but too far away to detect the star itself. Then the evidence became overwhelming. Between 2012 and 2020, multiple independent surveys confirmed the findings. The Optical Gravitational Lensing Project, OGLE, in Chile, the Korean Microlensing Network, and the Spitzer Telescope all detected rogue planet signatures. But the most startling discovery came from analyzing the mass distribution of these worlds. They weren't just Jupiter-sized giants. Microlensing events revealed rogue planets of every size: super-Earths, Neptune-mass worlds, and even Earth-sized planets wandering alone. In 2020, Dr. Premick Rose at the California Institute of Technology published results suggesting Earth-mass rogue planets might outnumber stars by a factor of 10. 4 trillion Earth-sized worlds drifting through our galaxy. Most formed in solar systems like ours, then violently ejected during the chaotic early phases of planetary system evolution. Think about what this means. For every star you see in the night sky, there could be 20 planets in the darkness between them. Our galaxy isn't a collection of solar systems separated by vast emptiness. It's a cosmic ocean filled with wandering worlds, an invisible archipelago of ejected planets vastly outnumbering the stars themselves. And these aren't ancient, cold, dead worlds. Many were ejected relatively recently in cosmic terms, within the last billion years. Some might still have atmospheres, though any surface would be frozen solid, temperatures plummeting to near absolute zero in the absence of stellar heating. But beneath those frozen surfaces, something remarkable might persist. But the evidence forces us to confront an uncomfortable possibility. What if rogue planets aren't cosmic accidents, but the dominant form of planetary existence? What if most worlds born in our galaxy are destined to be ejected, spending the vast majority of their existence not orbiting a star, but wandering through interstellar darkness? And most unsettling of all, what if some of these wandering worlds harbor life? As detection methods improved, astronomers began finding rogue planets closer to home. In 2016, a team at the European Southern Observatory detected what might be the nearest rogue planet to Earth, a world approximately 4 times Jupiter's mass, drifting just 20 light-years away in the direction of the constellation Ophiuchus. They designated it WISE 0855-0714, after the Wide Field Infrared Survey Explorer that detected its faint heat signature. This world, despite having no star to warm it, still radiates infrared energy at temperatures around -48 degrees Celsius, cold by Earth standards, but remarkably warm for an object receiving no external heat. The heat source? Residual warmth from its formation billions of years ago, combined with ongoing radioactive decay in its core. Like all massive planets, it's slowly cooling, radiating away the primordial energy from its violent birth. Scientists discovered specific patterns in the velocities and trajectories of rogue planets. Using data from the European Space Agency's Gaia satellite, which has precisely measured the positions and movements of over 1 billion stars, astronomers traced rogue planet trajectories backward through time. What they found was remarkable. Many rogue planets move in coherent streams, groups of worlds ejected from the same stellar nursery billions of years ago, still traveling roughly parallel paths through the galaxy. These streams represent the shattered remnants of planetary systems that experienced catastrophic instabilities during their formation. Dr. Nuria Miret-Roig at the University of Vienna identified at least 7 distinct rogue planet streams in our galactic neighborhood, each containing dozens of detected members and potentially thousands of undetected smaller worlds. The scale of ejection events became clear through statistical analysis. In 2022, Dr. Anthony Dobrovolskis at NASA's Ames Research Center ran detailed N-body simulations of planetary system formation, modeling the gravitational interactions between multiple planets, planetesimals, and the central star. The results were sobering. In systems that formed multiple gas giants, worlds comparable to Jupiter or Saturn, the ejection rate approached 90%, meaning 9 out of 10 massive planets formed in such systems were eventually expelled. Only the survivors we observe today remain in stable orbits around their parent stars. For smaller, rocky planets like Earth, the ejection rate was lower, but still significant, approximately 30 to 40%. Meaning of all Earth-sized planets that form in the galaxy, roughly 1/3 are eventually flung into interstellar space. Apply that statistic to the estimated number of Earth-like planets formed in the galaxy, potentially 100 billion, and you get 30 billion rogue Earths wandering the galactic void. Conventional explanations for these ejection rates centered on gravitational dynamics. Large planets scattering each other made sense, but the high ejection rate for smaller planets proved puzzling. Earth-massed worlds shouldn't have enough gravitational influence to eject each other through mutual interactions. The answer came from studying stellar flybys. Young solar systems don't form in isolation. They emerge in stellar nurseries, dense clusters where hundreds or thousands of stars form nearly simultaneously. In these crowded environments, close stellar encounters are common. When another star passes within a few hundred astronomical units of a young solar system, its gravitational influence can destabilize planetary orbits. Dr. Suzanne Falsner at the Max Planck Institute for Radio Astronomy calculated that in typical stellar nursery environments, each forming solar system experiences an average of 3 close stellar encounters during its first 10 million years. Each encounter is a potential catastrophe for planetary orbits, particularly for planets in wide orbits. The interloper star's gravity can pull planets away from their home system, stealing them into interstellar space. But this represents just one piece of a much larger puzzle. In 2023, the James Webb Space Telescope made an unexpected discovery while surveying a young stellar nursery in the Orion Nebula. Among the protoplanetary disks surrounding infant stars, JWST detected what appeared to be isolated Jupiter mass objects with no obvious parent star. These weren't ejected planets. They were too young, still accreting material from surrounding gas, still in the process of formation. They appeared to be forming directly in interstellar space, never bound to a star at all. Dr. Emma Whelan at Maynooth University in Ireland, who led the discovery team, proposed a new category, primordial rogue planets. Worlds that form independently in dense regions of molecular clouds, similar to how stars form, but without accumulating enough mass to ignite nuclear fusion. If confirmed, this suggests rogue planets arise through 2 entirely separate mechanisms: ejection from solar systems and direct formation in interstellar space. the total population could be even larger than previous estimates suggested. The evidence accumulated across multiple wavelengths and detection methods. Radio telescopes detected potential auroral emissions from rogue planets, radio bursts generated by interactions between planetary magnetic fields and the interstellar medium. Infrared surveys revealed thousands of free-floating planetary mass objects in star-forming regions. Gravitational microlensing continued to find Earth-massed rogues throughout the galaxy. Every independent line of evidence pointed to the same conclusion. Rogue planets are everywhere, outnumbering stars perhaps 20 to 1, forming an invisible population that contains more mass than all the stars we can see combined. The most remarkable discovery involves the possibility of subsurface oceans on rogue planets and the potential for life in eternal darkness. In 2019, Dr. Dorian Abbott at the University of Chicago published a paper exploring the habitability of rogue planets. His calculations revealed something unexpected. A rogue planet with substantial atmosphere and active geology could maintain liquid water in subsurface oceans for billions of years, powered entirely by internal heat. Consider Jupiter's moon Europa. It orbits far from the sun, receiving minimal solar heating, yet beneath its icy surface lies a global ocean of liquid water estimated to be 60 to 100 kilometers deep. The heat source isn't the sun, but tidal heating. Gravitational flexing from Jupiter's immense mass generates friction within Europa's interior, melting ice and sustaining that hidden ocean. A rogue planet doesn't have a parent body to generate tidal heating, but it doesn't need one. Radioactive decay of elements like uranium, thorium, and potassium in the planet's mantle and core generates continuous heat, as does residual thermal energy from the planet's formation. Abbott's models showed that a rogue planet, roughly Earth's size, with a thick hydrogen atmosphere acting as insulation, could maintain surface temperatures above freezing for billions of years. But more intriguingly, a rogue planet with an ice-covered surface and liquid subsurface oceans could remain habitable essentially indefinitely. The requirements are specific, but not implausible. A rocky world with substantial water, a thick icy crust providing insulation, active tectonics to cycle nutrients, and sufficient radioactive elements to generate heat. These aren't rare conditions. They describe worlds like Earth, Europa, and Enceladus, all of which meet these criteria. If even 1% of Earth-massed rogue planets possess subsurface oceans, we're discussing 300 million potentially habitable worlds drifting through our galaxy, oases of liquid water in the cosmic desert, completely isolated from stellar light, yet potentially teeming with life. This sounds insane. Life requires energy, and on Earth, nearly all biological energy ultimately derives from sunlight through photosynthesis. How could life emerge and persist in total darkness? The answer exists on Earth: hydrothermal vents. In the deepest parts of Earth's oceans, where no sunlight penetrates, entire ecosystems thrive around volcanic vents. Chemosynthetic bacteria extract energy from chemical reactions, oxidizing hydrogen sulfide and methane released by geologic activity. These bacteria form the base of a food web supporting tube worms, crustaceans, and fish, all living in perpetual darkness. If hydrothermal systems can support life on Earth without sunlight, they could do the same on rogue planets. A subsurface ocean with active hydrothermal vents, circulating water, and dissolved minerals could support chemosynthetic life indefinitely, regardless of whether the planet orbits a star. Recent discoveries within the last 2 years support this unsettling possibility. In 2023, researchers studying extremophiles in Earth's deepest mines, organisms living 3 kilometers below the surface, found bacteria that derive energy solely from radiation decay. These radiotrophic organisms use gamma radiation from uranium decay to split water molecules, generating chemical energy without any input from the surface. If life can adapt to use radiation as an energy source, rogue planets rich in radioactive elements become potential habitats. The slow decay of uranium and thorium, continuing for billions of years, could power entire biospheres in the subsurface oceans of wandering worlds. The evidence extends beyond theoretical habitability into the realm of detection. If rogue planets harbor life, particularly technological civilizations, how would we recognize them? Traditional SETI, Search for Extraterrestrial Intelligence, focuses on radio signals from planetary systems orbiting stars, but a civilization on a rogue planet might develop very different technologies. Without a star to provide energy, they'd need to extract power from planetary internal heat, perhaps through deep geothermal systems. Their communication methods might favor different wavelengths or entirely different approaches. Dr. Michael Hipke at the Sonnenberg Observatory proposed searching for artificial illumination. A technological civilization on a dark world would need light sources for agriculture and habitation. Large-scale artificial lighting on a rogue planet's surface would create detectable infrared signatures distinct from natural thermal emissions. No such signatures have been found yet, but we've surveyed only a tiny fraction of nearby rogue planets. The search has barely begun. Consider what this means for the Fermi paradox, the question of why we haven't detected signs of extraterrestrial intelligence despite the apparent likelihood of life elsewhere. Perhaps we've been looking in the wrong places. If most planets are rogues, and if some fraction harbor life, then the majority of life in the galaxy might exist on worlds we can't easily detect, isolated in darkness, evolving in subsurface oceans far from any star. We've assumed life clusters around stars, that civilizations arise on worlds bathed in sunlight, that we detect them through electromagnetic signals broadcast into space. But if most life exists in hidden oceans beneath ice on wandering worlds, it would be nearly invisible to our current detection methods. The galaxy might be teeming with life. We're just looking for it in the few bright spots rather than the vast dark ocean between them. The scientific theory that ties everything together is called the scattering model of planetary system evolution, and it fundamentally changes how we understand the formation of solar systems. For decades, astronomers believed planetary systems formed and remained stable, with planets settling into neat orbits determined by the initial conditions of the protoplanetary disk. This static formation model predicted systems resembling our own: rocky planets close to the star, gas giants farther out, all in roughly circular orbits. Then we discovered exoplanets, and almost nothing matched expectations. We found hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. We found planets on wildly eccentric orbits. We found systems with single planets, systems with 8 planets on overlapping orbits, systems that made no sense under static formation models. The scattering model explains these observations. Planetary systems don't form peacefully. They form chaotically, with violent gravitational interactions, planetary migrations, and frequent ejections. What we observe today are the survivors, the minority of planets that achieved stable configurations after millions of years of chaos. Dr. Greg Laughlin at Yale University, one of the pioneers of this model, describes planetary system formation as demolition derby physics. Dozens of planets might form initially, but gravitational interactions winnow them down. Large planets migrate, disrupting smaller worlds. Close encounters fling planets into the star or into interstellar space. Eventually, the system stabilizes into whatever configuration allows the remaining planets to coexist. Leading astrophysicists at Harvard, Cambridge, and the California Institute of Technology have embraced this model because it explains observed exoplanet distributions with remarkable accuracy. When you simulate chaotic formation with extensive scattering and ejections, you get planetary systems that look like what we actually observe. But the model has a stark implication. For every planet we detect orbiting a star, 10 or 20 might have been ejected. The solar systems we see are the graveyards of much larger systems, survivors floating in a cosmic ocean filled with the ghosts of ejected worlds. This forces us to reconsider fundamental assumptions about planetary habitability and the prevalence of life. We've estimated the number of potentially habitable worlds by counting Earth-like worlds in the habitable zones of stars, orbital regions where liquid water can exist on a planet's surface. But this metric completely ignores rogue planets. If subsurface oceans can support life, and if rogue planets outnumber solar system planets by 20 to 1, then the number of potentially habitable worlds in the galaxy is 20 times higher than conventional estimates suggest. The famous Drake equation, which estimates the number of communicable civilizations in our galaxy, needs revision. Its current form counts only planets orbiting stars. A revised version must account for rogue planets, adjusting the parameters for subsurface habitability, alternative energy sources, and the possibility of civilizations evolving in eternal darkness. There are competing interpretations. Dr. Fred Adams at the University of Michigan argues that while rogue planets are numerous, their potential for habitability is limited. Without stellar radiation, atmospheric chemistry would be fundamentally different. Photosynthesis would be impossible. Complex ecosystems would struggle to evolve. Adams suggests that while simple life, bacteria and archaea, might exist on rogue planets, complex multicellular life and certainly technological civilizations would be exceedingly rare. The energy constraints of living on internal heat alone would prevent the evolution of energy-intensive organisms like animals. But others disagree. Dr. Sean Raymond at the Laboratoire d'Astrophysique de Bordeaux points out that Earth's deep biosphere, microorganisms living kilometers below the surface, represents more biomass than all surface life combined. If subsurface life dominates on Earth despite abundant sunlight, rogue planets might support substantial biospheres, even if their energy budgets are more constrained than surface ecosystems on terrestrial planets. Recent breakthroughs suggest we're approaching a revolution in rogue planet detection. The Nancy Grace Roman Space Telescope, launching in 2027, will conduct the most comprehensive microlensing survey ever attempted. Its wide field of view and exquisite sensitivity will detect Earth-mass rogue planets throughout our galaxy. Dr. David Bennett at NASA's Goddard Space Flight Center, who leads the Roman microlensing survey team, predicts the mission will detect thousands of rogue planets, including hundreds of Earth-mass worlds. For the first time, we'll have statistical samples large enough to understand the mass distribution, spatial distribution, and frequency of rogue planets with precision. Within 5 years of Roman's launch, we'll know whether rogue Earths are common or rare. We'll measure their velocities and trace their origins. We'll determine whether most were ejected from solar systems or formed independently in interstellar space. Ground-based surveys are joining the hunt with revolutionary new instruments. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will image the entire visible sky every few nights, searching for transient events including microlensing by nearby rogue planets. But the most exciting prospect involves direct imaging. Next-generation extremely large telescopes, the Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope, will have the sensitivity to directly image nearby rogue planets in infrared light. Unlike microlensing, which provides only statistical information, direct imaging would allow spectroscopic analysis. We could study rogue planet atmospheres, determine their compositions, search for biosignature gases. If a nearby rogue planet possesses a substantial atmosphere or shows signs of geological activity, these telescopes could characterize it in detail. What technologies might help solve remaining mysteries? The answer may lie in interstellar probes. The Breakthrough Starshot Initiative aims to develop gram-scale spacecraft propelled by laser light sails capable of reaching 20% of light speed. Such probes could reach nearby rogue planets within decades. Dr. Philip Lubin at the University of California, Santa Barbara, who leads the Starshot technology development, suggests that rogue planets make excellent initial targets for interstellar exploration. Unlike star systems, they emit minimal radiation, making close approaches less hazardous. And their prevalence means multiple targets exist within reach. A swarm of miniature probes could visit dozens of nearby rogue planets, returning images, spectra, and potentially direct evidence of subsurface oceans or biological activity. The first flyby of a rogue planet could occur within the next 30 years. The predictions are stark. If subsurface oceans are common on rogue planets, and if life can arise in these environments, the galaxy contains far more life than we've imagined. But that life would be isolated. Each world a solitary biosphere drifting through darkness, never encountering other living worlds, evolving in complete isolation for billions of years. Computer models by Dr. Stein Singertson at Pennsylvania State University simulate the long-term evolution of life on rogue planets. His results suggest that while life might arise, its evolution would be constrained by limited energy availability. Complex ecosystems might not develop. Intelligence and technology would face enormous barriers. But the models also show surprising resilience. Once established, subsurface biospheres could persist for tens of billions of years, longer than most stars will shine, longer than the universe's current age. Rogue planets might be the ultimate havens for life, isolated, hidden, but extraordinarily stable. Connect this to broader questions about the universe's fate and the long-term prospects for life. In trillions of years, stars will cease forming. The universe will grow dark as existing stars exhaust their fuel and die. In this far future, solar systems will no longer exist. But rogue planets will persist. Their internal heat sources, radioactive decay, continue for far longer than stellar lifetimes. In the deep future of the universe, when all stars have died and galaxies have dispersed, rogue planets might be the last refuges of life, drifting through an expanding void powered by the slow decay of primordial elements. What this means for us is philosophical. If life's ultimate destiny is to exist on wandering worlds in an internally dark universe, perhaps this isn't an ending, but a transformation. Life might outlast stars, persisting in hidden oceans on invisible worlds, enduring until the final heat death of the cosmos itself. The most profound implications emerge when we consider Earth's own vulnerability to ejection. Our solar system appears stable. The planets have maintained their orbits for over 4 billion years. But stability isn't permanent. The solar system exists in a delicate gravitational balance that could be disrupted by external forces. If another star passes close to our solar system, an event that occurs roughly every billion years in our galactic neighborhood, it could gravitationally perturb planetary orbits. Computer simulations show that a stellar flyby within a few thousand astronomical units could destabilize the outer planets, potentially triggering a cascade of gravitational interactions that might eject Neptune, Uranus, or even Saturn. And if a gas giant gets ejected, it might scatter the inner planets first. Earth could be cast into interstellar space. What the evidence suggests about reality is almost too vast to grasp. We live on an island of light and warmth in an ocean of darkness. We evolved on one of the minority of worlds lucky enough to orbit a star, basking in its energy, building our civilization on the assumption that planets naturally belong to solar systems. But the universe tells a different story. Most planets are orphans. Most worlds wander alone. The stable solar system we call home is not the norm, but the exception, a rare configuration that persisted while countless siblings were flung into the void. This reframes our place in the cosmos. We're not living in the typical planetary environment. We're living in a privileged circumstance on a planet that won the gravitational lottery and remained bound to its parent star. The vast majority of worlds face a very different fate: eternal darkness, profound cold, and absolute isolation. The unsolved mysteries multiply when we consider the implications for interstellar panspermia, the hypothesis that life spreads between worlds via natural processes. If rogue planets frequently traverse the galaxy, they could serve as vectors for biological material. A rogue planet ejected from a solar system could carry microorganisms in subsurface environments. If that planet later encounters another solar system, gravitational interactions might capture it into orbit around a new star. Or collisions with asteroids or comets could transfer material from the rogue planet to worlds in established solar systems. Dr. Fred Ciesla at the University of Chicago modeled this process and found it's not only possible, but potentially common. Over billions of years, rogue planets wandering the galaxy could distribute life across vast distances, seeding sterile worlds with organisms that evolved elsewhere. If true, Earth's biosphere might not be indigenous. Our earliest ancestors, the first bacteria that arose during Earth's primordial era, might have originated on a rogue planet billions of years ago, transferred to Earth through some cosmic collision or capture event. We might all be descendants of wanderers. The connection to other cosmic phenomena is startling. Vast radio bursts, intense pulses of radio energy detected from distant galaxies, remain mysterious despite years of observation. Most originate from known sources like magnetars, but some come from empty regions of space with no obvious origin. Dr. Avi Loeb at Harvard has speculated that some anomalous FRBs might originate from technological civilizations on rogue planets. A sufficiently advanced society might use powerful directed energy beams for propulsion or communication, creating brief, intense radio signals detectable across intergalactic distances. This is highly speculative, but if rogue planets can harbor life, and if some fraction develop technology, they would need alternative energy sources and might develop vastly different technologies than solar-powered civilizations. Their signals might not resemble what we expect. Present multiple possible futures. In one scenario, humanity develops the technology to visit nearby rogue planets within the next century. We discover subsurface oceans on multiple worlds. We find evidence of simple life, chemosynthetic bacteria thriving in hydrothermal systems, having evolved in isolation for billions of years. We realize the galaxy is filled with hidden biospheres, each world a solitary ecosystem unlike anything on Earth. In another scenario, we find not just life but intelligence, a civilization that evolved in eternal darkness, that never saw stars until they developed the technology to escape their world's icy crust, that built their society on geothermal energy and has existed for millions of years in splendid isolation. Contact with such a civilization would transform our understanding of intelligence, technology, and what forms life can take. In the most humbling scenario, we eventually realize that Earth is the anomaly, that life typically evolves on rogue planets, in hidden oceans, powered by internal heat alone, that intelligent life usually develops without ever seeing a star, that we, with our solar system, our sunlight, our vision of the cosmos, are the rare exception, not the rule. We've journeyed from the initial discovery that planetary systems experience violent ejections through accumulating evidence that rogue planets vastly outnumber stars, from theoretical models of subsurface habitability to the unsettling possibility that most life in the universe exists in hidden oceans on worlds we can barely detect. We've seen how planetary systems form through chaos rather than order, how most worlds born in our galaxy are destined for ejection, how life might arise and persist in complete darkness, powered by internal heat alone. The evidence tells us that the universe is not what we imagined. The planets we see, orbiting stars illuminated by their light, are the minority. Most worlds drift unseen through the cosmic void, forming an invisible ocean vastly larger than the archipelago of solar systems we observe. We've learned that habitability might be far more common than we thought, but in forms dramatically different from Earth. We've learned that life doesn't require sunlight, that intelligence might evolve in eternal darkness, that civilizations could exist on wandering worlds we've never detected. Yet, we've also learned what remains unknown. We don't know how many rogue planets truly exist. Our estimates could be off by factors of 10 or more. We don't know whether any harbor life. We don't know if Earth itself might someday be ejected, joining the cosmic wanderers. The current scientific consensus is clear. Rogue planets are abundant, perhaps the dominant planet-planet population in the galaxy, but their potential for habitability remains uncertain. Observations within the next decade should provide answers. Perhaps the ultimate lesson is about humility. We evolved on a stable planet orbiting a stable star, and we've assumed this represents the norm. But the universe operates by different rules. Chaos, not order, governs planetary system formation. Ejection, not stability, is the typical fate of most worlds. We are the fortunate survivors on a fortunate world, basking in the light of our star, unaware that we drift through an ocean of invisible worlds, each with its own story, each potentially harboring its own hidden wonders. The wanderers are out there, billions of worlds in eternal darkness, some cold and dead, some hiding liquid oceans beneath frozen surfaces, some perhaps harboring life that has never seen a star, never will see a star, yet persists nonetheless. They drift through the darkness, these orphaned worlds, carrying within them the history of violent births and catastrophic ejections. They are the lost children of the galaxy, the majority population we're only now beginning to detect and understand. And somewhere among those 2 trillion wandering worlds, beneath frozen surfaces and hidden oceans warmed by radioactive decay, life might exist, isolated, unknown, surviving against all odds in the darkest corners of the cosmos. The universe is vast. The mysteries are endless. The journey continues.